welcome. And let's start on time.
No, 1 minute break for Sweden.
1 minute late, yes, yeah. So waiting until you had flipped over, that's true. I'm so sorry. Yes, I'll connect these two items, seismic imaging and optimal transport. So the effort here will be in the connection. I will not try to say too much about optimal transport coming here, where it is most of you know much more about it than me. And so we'll see rather how we need to modify certain items in order to apply optimal transport to the seismic setting. So this is the fourth lecture, and all of them are in some way connected to multi-scale problems. The first two were more general when the properties in the material or whatever it was of multi-scale nature, and the third had to do with the multi-scale coming from short wavelengths, high frequency wave propagation. So this part here, the seismic imaging, will deal with multi-scale issues, very much so, both in the terms of heterogeneity in the Earth and with waves going through that, and with high frequencies. It is a really low frequency, but if you make it relative to the size, it will be a high frequency problem. So we had one issue where we talked about waves going in a heterogeneous media, and you, for the long run, if you do long time estimate, you actually got not the homogenized solution of classical type, but you have to add terms that gave dispersion. So that happens here, and people look for these issues. We will not focus on that. So we'll focus on the inverse process. So the multi-scale issues will not be stressed too much in today's talk. It will be the inverse part. So we'll first introduce the problem as it is, and then see where optimal transport could fit into this setting, and then see what one need to do with optimal transport, or Wasserstein metric will be one important piece here, in order to fit it to seismic, and it's not a perfect match, so therefore there will be some questions there. So sort of in the development here, there were more or less two phases. When we had problems of simple nature, you can be quite close to the properties of optimal transport. And then when we went to look at more realistic cases to have implementation that industry would be interested in, then difficulties arise and one have to do more compromises. So the first part looks much cleaner. The second part, you would see, well, the difficulties enters. Yes. So the problem we are looking at here is seismic imaging. It could be over the sea. You have a ship goes there and it sends off a seismic wave by an explosion or by air gun, and the waves penetrate the earth and reflects back or diffracts back, and then you measure it afterwards. So what you have is a signal with a pressure vibration as a function of time at different locations. So that's what you have to work with. They could be on land also. It could be a vibrocyte that jumps up and down, which more fits to frequency domain. You have one frequency. This would be a broader bandwidth, but not too broad, because some waves they will be attenuated. You would like then to process these data so you get a picture of the Earth, you get the properties inside the Earth. What we are looking for here, we were looking for wave velocity, which is the one that is easiest to deal with, and that's what industry does today. The research is to be more ambitious, to look at anisotropies that actually comes out of homogenization of the material, and the most ambitious one would be to have full elasticity, all the parameters in the elastic equation, or the viscoelastic equation, because there is also damping. That's the challenge. And it's harder than problems like CAT scans, tomography, where you have the X-rays going more or less straight. You can use that. You can then get inversion formulas with radon transforms, etc. That would help you out. Here in this case, we are a setting where there's variable velocity in the media, and you have bending rays. You also have wave phenomena. You cannot look at it in the exploration part, you cannot look at it as rays in the geometrical optics setting, which you do if you do global seismology in this case. And here the wave plays a role, the bending of the waves plays a role. So that's the overall challenge in this case. So traditionally, one was only trying to do, using some guess or estimate of the velocities. You try to use a correlation between the forward and backward rays in order to determine reflection interface. So you propagated a wave field forward, you propagated backward, and you saw where they were correlated, and that would be at the place where the reflection occurred. This was called migration because the reflecting surfaces changed location due to what happened with the rays bending, etc. So now it's becoming more and more so that people are looking for full inversion of physical properties, including the velocity itself. So you solve for that together with the interfaces and the geometry, what happened. So we will focus on velocity estimation, but what they call in the business full waveform inversion. And that is done, let's see what we have, as a PDE constraint optimization. So you assume that your wave field are guided by a partial differential equation where you don't know certain properties. For example, if it's a wave equation, you don't know the velocity. So that would be the unknown. What you have is that you know the source, and therefore you could, if you know the unknown faculty, you could get the wave field all in here and also its reflection back on the surface. On the surface, you have the physical boundary condition, but you also have the overdetermined boundary condition because here's where the measurements are. So what you do is you match these together. So this would be an optimization to fit the parameters so that you go it, which is a standard optimization procedure. So in doing this, there are some steps where mathematics can play a role. One is to understand how you compare, and that will be today's issue. How do you compare one signal with another on the surface? What kind of metric would you use? And the other, of course, you have to solve the problems fast and efficient in the domain, and we talk about that in the third lecture in the series, and I will leave that out. The optimization part, I will just buy what they use today, so we'll not we'll deal with it, but we will not extend it. And we will use the model that we have a scalar wave equation. So we're looking at P waves or acoustic waves in the setting. The overall technology would be the same if you do anisotropy here, for example, or if you go to a more elastic wave equation. The difficulty is that you need, it becomes more and more ill-posed the more you look for, and you need more data, which they typically don't have today. So we'll stay there, and the phenomenon will be this. So what this would mean in the PDE constraint minimization is that we have given data, which is a measurement of in the pressure or some displacement on the surface of the Earth. And then you have the computed values that depends on your estimate or your guess of velocity. And you take some measurement of that in the A norm here, and then you may want to regularize the problem by having some property on the velocity field, like you would punish total variation, something like that. We will actually not deal with this term here for two reasons. One is that the industry very often doesn't do that. What they do is that they start with low frequencies and go to higher and higher frequencies. So that's the way they guide the minimization process. And the other is that we would like to understand what goes on with the metric here. That was the goal here, and then of course that is obscured if you have the other term. Many times this will be an improvement. So the measure of mismatch here, the standard has been for the full waveform inversion I've used 20 years or so, to use L2, or simple variance of L2 in this case. And this was about the regularization term where we knew that. why I looked at optimal transport here was that I did my postdoc in a geophysics setting, and it was obvious that L2 comparison of signals, at least if you do global seismology, doesn't make sense. The signal here, if you do the L2 difference with some measured thing where you have the wrong velocity, so this pulse arrives at the wrong time, it don't see each other in a sense. And at that time, Jan Bernier visited regularly UCLA through the 80s and early 90s, and he talked about transport more and more concrete every year. He came back, and I thought that was an intriguing thing to look at in this context. Of course, there's a big difference between probability measures and seismic signals, but still, this was, we talked about that in some way. But then the technology to do computation there wasn't there at this time. So then I put it aside there. Now, here, of course, what people do in order to determine where the earthquake is somewhere when you measure that, or if you know where the earthquake is, to take the average velocity or the velocity on where the wave had traveled to do that. You measure the time difference here. The seismic signals look more messy, and it's not clear that one event matches up with another event. So therefore you need a robust functional to look at the difference, the metric, that is nothing where you go in by yourself or by some artificial intelligence looking it up where it is. So therefore that was, so it would be a good candidate if one could use that in some way. And the Earth mover's distance, of course, or the Wasserstein distance over here, would be the cost in some way of moving this mass over to another location where the cost could be the one we would use, quadratic in the distance, multiplied with the amount that you move in the transport or in the plan that is there. So we can use the setting of Wasserstein distance, where you minimize overall possible combinations here between these two measures, and some metric of the distance mean in there. We will use the Euclidean metric squared, so it's a W2 norm in this case. So this would be the distance, and F is the amount that the plan tells us how to move from F to G here in this case. So this would be the metric that we'll try to use in the Wasserstein distance in the two, and we also use the square form of it. So in this case. Do I have a square up? No, half. Yeah, so we will actually square the one that we'll use in this case. And Wasserstein distance, when you're close together, then actually, when you have a good guess, then L2 does very well, and for that full waveform inversion. The difficulty is when you don't have a good guess to start. And of course, when they are close together, if I take two naive signals over here and just shift them, and shift is a natural thing. If there's a velocity change, you will then signal will arrive earlier or later, depending on what you estimated. And of course, then they behave very much the same. In least square, you square this and integrate. In the Wasserstein distance, you square this distance and integrate in the other direction. So they are compatible as long as you have a slope in the signal or in the function that you're dealing with that is bounded below and above in this case. But of course, if they are further apart, then the Wasserstein distance will measure the distance that it takes to move parts over here to this over there, depending on the shift over here. But the L2 doesn't see that. The L2 just, if they take this norm plus that norm, that will be the difference, independently of S, as long as you have support that is not overlapping. So therefore, it is a good candidate to do this thing. And one can see that in a little bit more realistic setting. So this would be a typical signal that is used by seismologists as a signal mimicking what happens in the real world. So this is a Sizelet or a Ricker wavelet. It's just the second derivative of a Gaussian. That is, so it's a symmetric mean zero, and then have these wiggles. So let's see what would happen if one compare the blue and the red dashed signal as a function of the distance between. And it's reasonable to look at distance. If we take constant coefficient solution of this, then of course the solution is given in an easy way for traveling waves. And there, when you change c, it will then be a shift in t. It arrives earlier or later. If you look at it as a function of x, it will be a dilation. A wave stretches out, of course, if the velocity is higher, and compressed when it gets lower. So these are good parameters to have as test. It should at least do well for these guys. So that's there. So if we now take these waves and look at it as a function of different shift and see what L2 different does, and this would be the image that you get. And of course it should be 0 when you have full match. As we said before, if they are far apart, you don't get anything. It just gives the norm of one plus the other, and then it interferes positively or negatively because of the oscillation. So you get a local minima here, and that is in the business called cycle skipping. You have sort of an oscillatory function, and you don't see, if you shift it to full wavelength, you cannot see any difference from the original state. So this is something that has burdened the business for some time. And people have come up with different ways to do that. So if you look at using the Wasserstein distance as a function of shift, it is, of course, just s squared, which is a perfect thing, at least in the model case, to apply then some optimization routine to find the minimum over here. So it was seeing this picture that said it might be a good. Yes, so so I'll talk quite a lot of the difficulty that the signal is not a probability measure. So the normalization is just reweighting them. So you divide by the norm in this case. So then it doesn't become a metric.
The signs?
Well, the signs, yes, so we'll come to that. So let's say we square it here. This doesn't work well, but it works well in this setting. So let's say we square it and then normalize them by divided by the norm, for now. We'll see, but it's a good point, actually. The whole business here with the trouble was mainly because of this thing that they are not probability measured.
Because this difficulty disappears if you were to take the one Morse contour of each with a Wasserstein distance, because it's a norm.
Yes, that's right. So and that people have used that. Then you run in, if you're then in a case where they are not positive, you run, it's not transport problem, and there's certain good property you don't get out of that. But that is a good candidate, and Viro and the guys over in Grenoble are doing this together with people here. So we'll reach that. Yes, that's true. You could reformulate it in a way. So that is where we are there. So that was the reason to start to look at that. And then the hidden difficulties is what Professor Lyons here just pointed to here, one slide ahead in this case, and we'll see what come to do that. So if you stay within this, then the Wasserstein distance is nice, in the sense that if you now do a dilation, you stretch the variable and compare it. So one signal, or probability measure in this case, is just stretched in the independent variable and then shifted in some direction over here. Then it is convex with respect to these parameters in this case. Also, if you do a local transformation, typically you cannot expect, of course, the measured data to be perfect. So if you have some variation over here, you will in a small area, you would then like to see that you can correct for that if you guessed wrong in the beginning in a convex way. And this is also a convex function of the difference parameter here. And we just modify it in a small area, and then due to the fact that we need to have a same measure, you have to change it in the other areas to do these things. So these are not a deep thing. It's a c-cyclic property that comes. So you will first see, since you have the optimal transport, is c-cyclic. So you think it's even easier, yeah?
Oh, yeah.
Yeah.
From the probabilistic interpretation, it's obvious.
Okay. But if you use this, you can show it in this way, because then the optimal map is, and then you show that the shift is actually the optimal map, and then you read it off in this way. And you do the same thing here. You can actually make it a little bit more ambitious, but it's roughly the same, that if you have a dilation with a positive definite matrix, it becomes then, if you normalize, if you write it on a diagonal form, and then go back again using this property in this setting, you come back and see that the shift is correct, you get that. And the same thing with this guy here, you use this inequality that exists for the W2 measure, and then formulate it in a parameter that fits that well, and then you see it's convex in that parameter and convexly rated the other. So all of these things follow from rather elementary things in this way. Another thing that is nice with the Wasserstein distance, where it's actually better than W1, is the robustness in noise. So you have typically your signal here, not your computer one. Well, there is also sort of numerical noise there, if you could call it. But the true noise, of course, is measurements over there. And it's not seen so by the Wasserstein distance. So if you take a signal over here and you add bounded, uniformly distributed noise, then you would see that the Wasserstein distance between these, even if you have an 001 noise over here, is very small, while of course if the variation is of over 1, or the standard deviation, then you would get an 0.1 result over here. And that has to do, of course, with emotionally, that if it is uncorrelated, you have nearby oscillation, and it doesn't cost anything to move, let's say, the positive to the negative in this setting. So you could do that in 1D. You have an explicit formula where an important part is the integral of the original form, and then you have one inversion. And of course, the integral in the discrete setting would be a sum, so we'll be getting the mean, and the standard deviation will give you a square root error. And of course, now it was a W2 norm, so we square that, and then it happens. So in 2D, one can do a domain decomposition argument, maybe do I talk about this? No, argument so that you can do 1D results and couple it to 1D in another way, and the optimal transport is better than doing 1D first and the 1D in the other variable. And that's, so it is very robust here. If you do W1, you would get half there in this case. Well, in 1D, if you do this thing, I don't know if you could, if what happens.
It's a weaker distance, so it should see noise even less. It cannot go worse.
I mean, if you use this, the thing is that the cancellation, the distance is squared in the cost function there, and it's not. So if you take the example that
well, it depends on how you define on sign stuff. I mean,
yes, that's right. So in this case, you just you perturb around, let's say, 1 in this case.
Stay positive.
Yes, stay positive. So we have a Barnum measure. So otherwise, we will not have this case. So
I'm very much surprised.
Oh yeah, but take the example. Let's say Villani has not for noise, but he just took the oscillations to be plus minus delta. In this case, around 1, yes.
Oscillating like 1 over n.
Oscillating 1 plus delta, 1 minus delta, 1 plus delta, and then.
In 2n intervals in 0, 1.
Sorry?
In 2n intervals
yes.
in 0, 1.
Yes.
It's 1 over n, the derivative on an L1 function, so the W minus 1 norm is 1 over n. I don't understand that.
So the cost. Let's see here. Yeah, it looks like that. Yeah, I haven't looked at it. Here, it's a square. Yeah,
okay, so
yeah.
I'm sorry.
No. This is.
I just want to.
Yeah.
Don't worry.
Yes. Yeah. So let think about that. of course,
But it's an interesting statement, that it sees much less noise.
yeah.
It's a weaker way of measuring the size. So
Yeah, it should be, that's right. So the square root is squared over here. And of course, if you square the other one also.
So I would expect that
Yeah, no,
if
it
you were
probably.
to take an h minus s norm with s large, it would be
Of course.
It would be even smaller.
Yeah. So you because you integrate once more in this case. Maybe it's the square root here that I thought about in the W1. So it should be, you add it up.
Sorry.
No, I tried to understand it myself. Yeah, it probably is the same actually. Yeah. Because, yeah. So, why we started with this was the first input was Jan and nothing happened because we didn't have the tools. The second was that we got a postdoc, Brittany Froese, that had worked with Alan Obermann and Jean-David Benamou over here, and they had then, in her thesis and also the joint papers, had a method that worked quite well using the Monge-Ampère equation. So then, already before, of course, the connection between optimal transport and the Monge-Ampère equation was done over here, where a lot was done with Jan in this way, so that when we are looking at the Wasserstein metric, you get automatically the transport plan as a gradient of the solution to a Monge-Ampère equation. So this connection over here. And then you had a nice way without optimization, without using the Hungarian algorithm also to get this. And in principle, if everything works out, this would be then a good way to do that. And what they had done there was building on earlier results about the PDE's properties overall that then Takis and Guillaume Baldi looked at and gave a monotone thing, monotone difference approximation would do well in this setting. The monotone scheme here that they had, and she had there, so they had already something to deal with, needs a little bit of explanation in general. We will not do that here. One important feature was the difficulty in order to get monotonicity out of this term here, the mixed derivative term. If you do a standard approximation, doing a divided difference in one direction and in the other, it will not be monotone. And if you do that directly there, it will not work well. So what the observation was here, that you could do this by taking the divided differences, second derivative, in the directions of the eigenvectors of this way. So we adapted. It will depend on the solution, what you would do. And they restricted the direction to be living on the grid, so you had a finite number direction depending on how you could do that, and you can come close enough to more monotonicity, and that would be the basic thing, and then you do some improvement around that. The only thing we looked at here was that we had an outer optimization in the full waveform inversion, and that causes, of course, difficulties if you have a stencil that changes style during the calculation. So you would get less regularity. So one can do that switching from one direction to another is done in a smooth way, as we have done past when it comes to nonlinear conservation law, where you do upwinding in one direction versus the other. And then they had tests, and we do also tests where the convergence, you can relax the monotonicity to get a higher order method, and still without proof in this case, but still do well. So that would be the background on that setting. So we'll take a look at using this tool, the Monge-Ampère solver, in the connection of inversion problem. And we can also look at registration, where you see a good thing, of course, with the way of deriving the Wasserstein distance this way is that you actually have an explicit form, the gradient of the map itself. See if you can use that. So this would be the case. So the first case here would be that without a wave solver, you just use ray tracing, and you could have positive measures to do that. So you get typically a picture like this where you do many time traces. That is, that here the offset would be the difference between the source and the receiver. And of course, and the time goes down like this. So if they're on top of each other, they get a reflection that is coming earlier at time than if you have this distance larger over here when S and R is larger. So this is typically what it looked like. This would be reflection in the first interface, in the second. And then you have to play around with these variables in order to adjust them so that your measured data would be the same as the computed data we're based on these guys. So this was the first test, and the thing that it looks good is, of course, that if you do it with L2, then, and choosing 2 out of these 4 variables, you get a much messier map where you are easier trapped in ridges rather than converging into the bottom ridge in this. You typically have not a very well-defined minimum because if you don't have too much of an offset, you cannot see the difference between having a higher velocity or a shorter distance to the reflector. It would be the same in this case. Also here, without doing much more, one could use a standard search algorithm and have, let's say, the velocities. And here we have using the wave equation. So these were different velocities in a material, and you start with a wave over here. You measure the wave reflection as a function of time and location, or rather the offset, the difference between source and receiver. You start with a certain velocity distribution, that is, you get your first guess that it shouldn't be like that, and then you compute and get it like that. And this would be the convergence history measured in the Wasserstein distance, and this would be how the different velocities adjust to each other. So these were everything worked fine in this case. And this was done actually by squaring the signals in order to get them positive, and then normalize them with the integrals. So in order to do more, one needs to have a better way of doing the gradient and then the numerical way of doing it. And that is what was done within the full waveform inversion. You do a joint state method in this particular case. So, and then from that you get the Fréchet derivative, the gradient, which you then use inside a Quaterniusen method. So you have the gradient and you use that and then you update with a low rank update something that in the end would approximate the full Hessian, as you do in Quasi-Newton method. And this was the technique Broyden, Fletcher, Goldfarb, somebody else, with a finite length that was used here. For L2, it's easy to see there your functional that you're minimizing with respect to the velocity, or rather slowness, in order to have it linearly sitting in the equation. So these are the one that you would like to get the derivative with respect to n. You would like to get this guy, the gradient. And if you write this and in terms of the inner product, take the derivative inside, use a chain rule, and then in order to get this explicit, you get one of the wave operators thrown over to its adjoint, and then you get in the end the expression over here where you correlate. So this just comes out of taking the derivative here and fooling around, where you correlate the forward solution from your source and in the full space, integrated over time. You correlate that with solving backward in time, the adjoint, starting with the residual, that is the difference between the forward computed solution and your measured data. in this case. And the second derivative it just comes because m is sitting in front of the second derivative in the wave equation, the slowness in this case. So this would be the one, the gradient that you do, and you discretize, of course, by taking numerical quadrature in order to do this thing. And then you feed that back. It becomes a little bit messier in the Wasserstein distance thing, but you have anyway an explicit form to do this in the way based here on the Monge-Ampère solution or the transport map. So that was based, and now one can upgrade the game and use, instead of 4 or 9 or so unknowns, 10, 100,000 in this case. Still, this is still a problem in this case. Come back to this. But I'll just say that the one test that everybody has to do is this Marmousi model. So here is a velocity distribution. What you would get, you have to start with something. And let's say you do something like that, which is well smoothed out, so none of the details are in this thing here. And then you run your algorithm. So what would happen, this was the original model that you would like to reconstruct. And this is what you get by using the Wasserstein metric as your mismatch tool, and then the gradient based on this thing in the minimization. And this is what you get if you do L2 with this start. So in order to use L2, be efficient, you have to do something that is much closer to the truth when starting this. So this is a good test. It was a good example. In this case, we just added a constant and then normalized it in order to get the measure the metric or rather to fit into the Wasserstein metric conditions or being a positive measure. So that's the setting over there. And that is as far as we can go along there. And now let's take a look at the registration. That is comparing two sets. Let's say this will be one and another. If I use the Monge-Ampère equation over here, I get the gradient of u looking like that. It tells a little bit how I would move in an optimal way this guy to fit this one and this guy to fit the other one. And that's sort of an advantage, of course, there. The applications are in two ways. One is you have different ways of measuring in the Earth. Seismic is the most common and well, but sometimes you would like to calibrate if you have a well-known field where you actually have drilled and know what it is. So you would like to see which event matches to which other event. You would like to see the connection between this guy and that guy where they're sitting. And also you could have an electromagnetic inversion, which is even cruder, but you would like to compare the different features and see where they come from, so you can compare. The other is to monitor a reservoir where there is actual geological change. You can see how it changed as a function of time. Either how you deplete it by taking oil or gas out of the ground, or the other way around. If you do carbon sequestration and would like to be a good guy and put the CO2 down there, you would also want to monitor the change. The registration is then a good way of doing it. Here again, it is a little bit, you cannot use it directly. So let's say we had this layer that were distorted by a rotation in this way, and then I would like to find the map back so I can go from here back to these things. If I just use directly the Wasserstein distance and get the gradient, then out here where there were very little mass, there still is transportation, so that it doesn't affect the overall mass transport or the Wasserstein distance so much, but the vectors could be large because they move almost nothing from one point to another. So therefore one has to approximate and truncate in order to get rid of these moving masses. If they're very small, it doesn't cost to move them around. You would see this in the field, and if you then iterate in that, you can get a good wave gap. But also there, the clean let's say, application of using the optimal transport is not what you're interested in. If you have, let's say, two events looking like this, and you have two other events sitting there, you would like to have the contact, this moves to the other. But if the normalization is a little bit off, then you have to move stuff from the other, and that messes the whole thing up. So we do that by iterating. Not clean, but one can do it from this way. So that's a difference there. Now, if I would like to do more realistic example, then the good thing is that we were able to do that. The bad thing is that one goes further away from the nice original setting. So one thing is that it turned out that 1D optimization, just do it in time and then add them up. So you do, let's say, Wasserstein in time and L2 in space. You just add up the W. Works as well in this case, in the practical setting. It's still within the optimal transport. The other is about the normalization. And there, the normalizations that give you convexity for shifts and dilation were not doing well in the full setting. Other normalization that doesn't do so well for with respect to convexity with shift and dilation did better. So that is a dilemma in there. So we'll take one at a time. So the mismatch would be to use that only do the distance in the time direction for a fixed x location, fixed point on the surface, and compare, and then you add them up, square and add them up in this case. So this was B, and then you can use the explicit solution. And the one advantage in this is that it's very much faster, and that was something they complained about in the real world. And the other is that quadrature is very accurate, it's very robust. Solving Montchampère equation is still a challenge. And you have trouble with when you lose ellipticity, and you get numerical artifacts coming out, which are just errors, which can be controlled, but they'll still mess up this optimization loop. So therefore it works.
That joint equation is even worse, because it's, you're using the linearization of the Montchampère equation,
yes,
which means computing the second derivative of the solution.
Yeah, you use a linearization of that, that's right, yeah.
It's a degenerate equation.
Yeah. So, yeah, that's right. So it's, of course, the monotone approximation is a little forgiving, but it's a big mess. That's true. Yeah.
Have you tried, instead of normalizing, let's suppose that all the signals have been made positive by adding a constant. That part is fine. The division by the mass will create lots of nonlinear artifacts. Have you tried to add to? So let's assume that all those integrals are bounded by, let's say, 1. Yeah. Okay, or 10, whatever.
Yeah.
By adding the complement of the mass at a point very far away with a Dirac mass. So they become all normalized, and that shouldn't be too much a problem. Of course, there will be some mass going to that symmetry state. But in some sense, if you don't have the priority measures, you're going to have some artifacts.
Yes. And actually there was also a problem with adding a constant, because you lose convexity with respect to shifts. So if you have a oscillatory function and you add it up, then you don't have this property any longer when they come, so you get a little bit back. So we'll see a little bit. The comment there is something that I just about looking at more innovative ways of defining the metric, having Wasserstein as a component, but doing things. That's sort of the last line in conclusions here, so we'll come back to this. And that has to do with unbalanced in different ways doing that. So the story here is that now we would like to have the people in seismology industry happy, and so we are willing to compromise of our honor. So in this case,
or what remains.
Yeah, water that is gone. Yeah, that's right. So one thing is to do it in 1D. It's very fast, robust, good. It's just summation and then inversion. So it's an n log n process when the inversion is done with quicksort or whatever you call it, half dividing it. So this is a good part. Corresponding, it also has a cleaner form in this case for the Fréchet derivative used in the adjoint state method. So it becomes much more robust, much easier for them to implement in their codes in this. So now we come to the normalization thing. The types of normalization that people have used and tried, and we have tried. So one thing is always like this, which you talked about. But then you could square it, and of course then it becomes positive. You could take the absolute value, you could use a positive part of it and add perhaps a positive and negative part. And that's what we did in the earlier case when we didn't use the adjoint state method, had few variables. In the first test with Brittany Froese that was doing it before Jonan and Yang come in. And others that works much better, like for instance adding a constant, which then is large enough in order to handle this. You lose this nice theorem, well, simple theorem, of convexity. But in practice it works much better. So we'll take a look at why this is the case a little bit. It's not completely convincing. So this is a problem where you have to adjust to reality in some way, and this is other aspects that play a role. So the thing is that discontinuities in derivatives here with this guy, and also when you do f plus and f minus, together with optimization loop, and is a problem when you do the derivatives, etc. So that messes up the optimization process. The squaring, of course, also increases the frequency. So it's easier then, like if you square just a sine function, it's easier to get trapped since we don't have the full convexity in this case. And furthermore, it is not a bijection. I mean, the thing is that if you match the squares, f squared and g squared, you don't know whether f and g are the correct one, because these were the signals, of course, with signs in this case. So that doesn't work so well either. On the other hand, the linear scaling that failed on the test of convexity in this case, when you do a shift, it is pretty good in other tests. So if you do a wave field here, where you just have a linear increase in velocity, and do a look at the functional or minimizing the difference between the truth and something else. So you have a linear velocity, you have velocity here that depends on a constant and another constant times z, so it's linear there. And then you would like to look at the L2 norm compared to a constant, and the Wasserstein distance over here. And here you have a much more convex setting. So even if it is not convex with respect to shift, this is a good thing. And this is an example we took from another group here that do W1, that's located in Grenoble. And they have started to do this after we first introduced it, and they are using W1 and the solvers that I didn't know existed at that time when I started.
On the other hand, there is another problem with, I was advocating W1,
yeah.
But there are difficulties with the adjoint problem, because the differentiability will involve, having like bounded variation minimization type equations, like divergence du or
yeah.
du. I mean, you're going to have to solve this, and that's not entirely, especially if you want to compute some Hessian and so on.
Yeah, I mean, you explicitly don't compute a Hessian, but you do it implicitly through the quasi-Newton, so you need it to have good properties. And that's what they do. Well, so I don't know the details, because of course there is a fast development of numerical methods for both W1 and W2 going on over here. So I don't know where they are. ultimate results are a little bit better doing it the way we did it, if you look at it from a seismic point of view. So Biro actually at the conference, he stated that the cycle skipping is no longer an issue because of this thing. Now it was a meeting where there was a lot of math people, so I'm not sure he was completely honest, but at least I like to hear it. Yes, in this case. So there is another feature which has to do with this transporting things in an artificial way, where there is a clear connection between events here and another event at another setting. If I now take away the negative part or square it or something like that, and then I would like to connect the left part of the signals and the right part of the signals together. But if I do it so it's positive measure, then and I have an error, meaning that the mass of this part and that part do not overlap. So there would be, in any transport form, there'll be a transport in between these two masses. That causes problem. If I now do use the add a constant, then because typically seismic signals are around the ground state, which you hit and come back. So the mean is typically very close to zero. And that means that very little is transported from sort of one event that includes 10, 15 oscillation and another event that can do it. So that could be a feature in this setting. That is something we just observed, nothing we have put into a mathematical form. So a compromise is, and works quite well, which is a function that is lifted up a little bit and then biased. So you get something that connects over longer time and reduce the effect of shift. So the function would look like this instead of going all the way down. So you bias that by using linear on one side and exponential on the other side to taper the negative side up. So this is a sine sensitive one, and you add up the two, then it is almost convex, but not completely. And this is a one we used quite a lot in the end. Many of the others where there was sort of a compromise between these settings. Very engineering style of doing this. So if we now take the test using these ideas, you could see that the W1, W2 misfit function here, trace by trace, does a little bit better than if you use it globally with the Beauchamp equation. I think mainly it doesn't become because of the norms themselves, but the way it is done. There's a lot of numerical artifacts in here, and that messes up the calculation of the gradient and thereby the other method. But in practice, that's what you see. In other applications, this happens also. So this is solved, so it's a challenging problem, starting velocity. And we can go a good inversion according to the people in seismology. This is what would happen if you do a full global with a Montchamp solver. And this is what you happen if you do L2. So the advantage is quite good in this setting. Here a problem where it's a transmission only. So you have sources here, you have a receiver below. It's a lab test example, the Camembert. And there is the only one you can see a little bit more because this is coarser. So you are easier to solve the Montchamp equation more accurately. You can over discretize, and there you can see a little bit better color representation. That is, the accuracy in a decent norm would be a little bit larger by doing a full 2D Wasserstein metric versus L2 doesn't work at all in the setting there. And also you can add noise, of course, as we saw, the sensitivity was less. And here is a reconstruction, even with a very large amount of noise, of much larger, but uncorrelated now, than the signal part in this case. So and this is in the data, so it behaves extremely well with respect to that, which is not done. The final thing is a little bit fun, and that is that using the optimal transport idea here actually turn out to work good in a setting which has nothing to do with cycle skipping, nothing to do with the problem of L2, that you can get interference and do So this was recovered with bow layers. So if you take a problem, I go back to the original case that I had to start it off to say that seismic inversion is harder than tomography in this case. So the question is, what you get is, of course, information back from refracted or diving waves like look like this, and then reflected waves like that. So it seems counterintuitive that you can get anything below the lowest interface, because there is no wave coming back. So let's say you start with a guess that is constant, then of course these waves go down, that is your simulated wave, and nothing comes back. And also in the truth, because there is nothing, it's a constant medium down below, so nothing sort of turns back, no information is back. So it would be counterintuitive that you could actually get something out of that, because there is no returning wave. But you actually can. Which is interesting in itself. So here is the true velocity model. You have water, you have the first material that you know. So you have water, first material. So this is the initial guess. These are the things you know. And then you have a layer that you don't know. But of course there is a reflection there in this layer, but nothing from below coming back. So then you run, the data comes from this model, your first attempt comes from this model, and then you try to match them. And what happens is that you find the layer, because you have to correct something, and you have the forward and backward, so they correlate at this interface. So you get a gradient that is different from zero at the velocity there, and you get this surface there. In the W2 case, that's what happens, and nothing more. In the Wasserstein distance, you start to recover the whole part below this thing. It is not so strange if you look at the cartoon case over here. So this would be the velocity as a function of depth in this case. So you have the layer over here. You don't know what happens. You just see that there's a reflection over there. You correct for that. And then you correct locally. That's the only thing that you can do, because you don't have anything. And that happens from the correlation of the forward and adjoint problem. So you get a correcting layer. And then, of course, in the truth model, there is no end to this layer. So you get a reflection in the second layer that you artificially have done that shouldn't be there. And then that is corrected in a different way. So that's why you fill out the domain. So not knowing, not having anything coming back is also information that there is nothing there. And this is what happens in this case. What is the difference between L2 and W2 in this case? So what happens is that during this correction, you get a fill-in with velocity by the minimization process behind the layer here in order to compensate, so the layer looks like that. And if I look at the profile, it looks pretty linear, so I just draw this over here. And now you measure the reflection in the dashed line only happening here, and the reflection with the measured, with the computed setting, which has sort of this ramp velocity coming back. And there is a reflection in coming from the ramp and from the discontinuity in the derivative of C over there. And if I now, these are very small because it's not a sharp jump, it's only a jump in the derivative. And the L2 that measure then the amplitude that is very small here, in the L2 setting, you square in the norm, so it's very little. So the L2 doesn't see this, and it believes in a sense that there is no reflection coming back here, and it flattens out, so it stops. It doesn't continue to improve. While the W2, of course, the distance here increases, and you only have, it's not squared in the amplitude direction, it's only squared in the distance direction, and that is then a large difference, so that you get a decrease even when this is quite flat, and it goes all the way slower and slower, but it does that. That's where you get a recovery over there in this setting. Yeah, and that is coming back to the original setting. It's a very strong difference in performance in these settings. If one now have waves coming back, so we do the same scenario, we have a layer that you know and a layer and a discontinuity that you don't know from the beginning. But then you have, in the truth model, you have increased velocity. So you have the reflection going on here, and then you have diving waves or refracted waves that bend around here, increasing and come back. Then the recovery is much better. So you get the first process as we had, and then because then you create these diving waves, so the recovery of this is better in the W2 setting. L2 doesn't do that at all. It doesn't see this, and that is because two reasons. So one is that the first the layer is not developed below the reflector, and the other is that the diving waves that are there in the true model, they would be way off what you have in here. So again, L2 measures things that are far apart. One is one is way off from the other. So the compact support of the computed wave is different than from the measured wave in this case. So therefore, it works quite well. And this can be seen also in model. This is one of these models that people use in the business, where you have variation in velocity, and there's some salt inclusion down there. And this would be a starting value where you don't know the salt inclusion. So it's just the average smeared by the background in this case. And then, as we saw, the L2 wave in migration style from the first correlation gives you the surface of this, no, the W. The L2 gives you the surface, the W gives a little bit more. But if you run longer time, there are diving waves that helps the L2, but you don't get at all the recovery that we saw in the other way. So these will be examples that are good in the setting. So what one can say, it plays an important role here as a source of inspiration, I would say, for the algorithm, rather than in a more concrete way. And it is now taken up by research group, not only the Vero and his people over there in Grenoble, but several places in the US are using it also in the UK and Cambridge. These are sort of the big meetings, Society of Exploration Geophysics meetings, that is once a year. A lot of people, 20,000 people coming to these things. And this year, for the first time, there were industry reporting on using optimal transport-based full waveform inversion, and there will be also in the one in the fall. So it's been useful in that. Now, if one would like to go further, this was rushed in a way in fixing engineering style, then one would like to go back and look at things, for example, the things that became a problem. One could think of unbalanced optimal transport in some way, or incomplete optimal transport in some way. And one can also think about other distances than just the square. So you taper off the dependence on which one can do in 1D at least. So there are, I think this was rushed in order to come to see that it works. And it's Yunnan Yang was the only student that I sort of started out in math and actually did an internship where the company used the model there in a way short period of a person. But now it's time to go back and look more deeper into the process. Thank you. That's it for the program.